So today, we're going to continue talking about this chi-squared test because there's a second version of it. This one is going to test for independence, so this is going to be a bivariate test. So sometimes we want to examine the distribution of a single categorical variable in a population. That's the goodness of fit test. And other times we want to see if the distribution of two variables suggests that one variable has an effect on the other. That's going to be the independence test. This allows us to determine if there's convincing evidence of an association between the variables in the population at large. I'm going to say right now, I'm going to be very picky about the vocabulary you're using for independence. The word that I do not want to hear is correlation. So if you say association, you say correspondence, you say something else, relationship, all that is fine. You say correlation, I'm marking it wrong. Correlation has a very specific meaning in statistics. We're not talking about correlation here. Everybody's clear? Okay. So the chi-squared test for independence. When dealing with two qualitative variables, we're going to be using the chi-squared test for independence. What this means is that the main objective of the test is to show that our two qualitative variables are independent of one another. Thank you, sir. How we use that objective and how we interpret our results, does that matter? Does that matter to the mathematician? I don't know, whatever. It's not English. The main or null hypothesis can always be stated in the following manner. Variable x and variable y are independent of one another. So when you're writing your null hypothesis for an independence test, they all sound the same. Variable whatever and variable whatever are independent of one another. So again, here, vocabulary matters. If you use other words than independent, I'm going to mark that wrong. So if you say related, correlated, not caused by any of those things other than independent, is going to get marked wrong. Just to be super clear, for the chi-squared test for independence, you have to use the word independent in your null hypothesis. Got to see it. Should be easy to remember that, but, oops. Oftentimes when performing an experiment, it is helpful to also define the opposing or alternative hypothesis. So that would be variable x and variable y are dependent on one another. The only other option I would accept there is saying not independent. Okay? So again, for the independence test, null is the two variables are independent of one another. Alternative is the two variables are dependent on one another. Hopefully, again, should be easy to remember that. The actual math involved here is pretty limited or basic. All we're going to really check is that our two qualitative variables, for independence, we're going to do that to basically see how far away our data is from some expected data set. So it's the same idea as the goodness of fit test, but the calculation will look a little bit different because here we have two variables going on instead of just one, right? So what we're going to end up doing is calculating the chi-squared calculated value. And basically, the smaller the chi-squared, the better our data fits. So it's more likely that our null hypothesis is correct. So that smaller that chi-squared value, the more likely your two variables are independent. That means one is not having an effect on the other. So first thing we need to do is organize our data into a two-way table. So let's say have a survey comparing the average number of hours a person sleeps with their overall weighted GPA. This sounds familiar. So here we've categorized our GPAs into less than 3.5, 3.5 to 4, and more than 4. And then our hours of sleep to less than 5, between 5 and 6, 6 to 7, and then more to 7. And then we organized our two-way table based on the results of our survey, right? So while both variables, the average hours of sleep and weighted GPA, are quantitative, we made them qualitative by arranging them into this two-way table, right? Please note that this table represents our observed counts. So this is what the result from our survey is. We're going to show you how to create, we're going to have to create an expected counts table from this information, right? Because in all reality, the chi-square test is just comparing observed counts with expected counts, right? So let's show you how to create that expected counts table, because how many expected counts should we have? I need one for each of these boxes. So there are 12 boxes here. So I should have 12 expected counts, right? Because there's 12 qualitative responses. You know, your sleep is less than 5 hours, but your GPA is more than 4, right? That's one possibility. Okay. Once we found our observed, or once we have our observed counts organized into a two-way table, we need to find our expected counts. These are the estimated frequencies for each group based on the observations you have. So the expected counts are found using probabilities and average and come from your observed counts table. For example, take the group in the upper left cell, right here. That's less than 5 hours of sleep and a GPA of less than 3.5. Based on our data, we'd expect that the probability of a randomly selected student getting less than 5 hours of sleep would be 22 out of 100 or 110. Everybody's okay with that? And we'd expect the probability that a randomly selected student would have a GPA of less than 3.5 to be 30 out of 110. So the row total divided by the overall total, and then we had the column total divided by the overall total. So the probability that we would select a student that has both of those two attributes would be the product of those two probabilities. So again, it's column total divided by overall total times row total divided by overall total. But we don't want just the probability, right? We want the actual expected count. So what I'm going to do is I'm going to take that probability and multiply it by the total again, right? Because that'll give me then how many students I'd expect to meet both of those two criteria. So this would simplify down to just 22 times 30 over 110. Or really what we have is column total times row total divided by overall total. And that's going to be our formula. So again, these expected counts are not probabilities anymore after we multiplied by that extra 110. These are expected outcomes. So we'll do that same formula then for every cell in our table. Everybody's okay with that? So quick pop quiz. How would I calculate the expected count for someone that sleeps 5 to 6 hours and has a GPA of 3.5 to 4?
28 divided times 45 divided by 110?
Nope.
Oh,
Just use the formula.
8 times 45 over 110?
There you go. Thanks, Isaac. Everybody's okay? So really easy to do, easy formula to remember. Diego, you're doing too much. You calculate the probability, and then you have to multiply by the 110 again, and they just kind of cancel out. It's just easier to just go with this formula. That's what we derived on the previous slides. Okay. So far, so good? So this is what I got for my expected counts table when I rounded to 3 sig figs. Remember, again, the totals should be blank, right? All right. So what do I do with this now? I have an expected counts and I have my observed counts. The next thing we need to do is confirm that our data is even going to be valid to use. What 2 criteria do we need to meet? The same 2 criteria as the goodness of fit test, still a chi-squared, randomness and large counts. So the large counts is easy. Do we make that? If I look at each cell, the expected counts in each of them is greater than 5. So we're set there. And if we talk about randomness, if this is high school students, we had 110 high school students. Is that less than 10% of high school students nationwide? Absolutely, right? Okay. Now we can begin to calculate this chi-squared statistic. We have our observed counts and our expected counts. We've satisfied the randomness and large counts criteria. Let's just go ahead and do the calculation. So what we're going to do is we're going to do observed count minus expected count squared divided by expected, and we're going to sum that up for each cell then. So like 3 minus 6 squared divided by 6, 6 minus 7.64 squared divided by 7.64, and we're just going to keep adding these up over and over and over again. Blah, 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 blah. So here we go. So it's going to look like that, right? Katie. Yep. Ah, where did it go? Sorry. Okay. So just from at a glance, which cell does it look like is going to contribute the most to our chi-squared number? Well, it's going to be the one where the observed count differs the most from its expected count, right? So at a quick glance, that appears maybe that it's this cell here, right? Do you see anything worse than that? 5.8 is a pretty big difference. And which cell would contribute the least to the chi-squared? Well, the one that's the closest to its expected count. I don't know, is it this cell here? The 9? Oh, yeah, perfect. They're exactly equal. Way to go, guys. That's using your noodles. Okay, so we did this calculation. And what this table is just each one of these calculations here, right? So like 3 minus 6 squared over 6 is just this number here. 6 minus 7.64 squared over 7.64 is just this number here. All I'm doing is just storing these somewhere so it's easy for me to grind out the numbers later on. We'll do this to calculate for your IA. And when I add up all these cells, we get about 12.6. So again, that's fine, but what do we compare this to? We either need to come up with a chi-squared critical value to compare this to, or we need to calculate the p-value associated with this chi-squared number, and then we can compare that to the level of significance, right? Same idea as before. So again, to compare or to get a chi-squared critical value, we need two things. We need a level of significance and we need a degrees of freedom. So the degrees of freedom is how many independent choices you can make when assigning your variables or groups. So if you think about the situation where we had categories, we said the degrees of freedom is the number of categories minus 1. Because, if I have 6 blanks, well, for the first blank, I have 6 choices. The next blank, I have 5 choices. But when I get down to the last one, I don't have any choice. I just have one place left and one place to put it. So that's not really a choice anymore, right? That's why it's the number of categories minus 1. For the independence test, the chi-squared is going to be the number of rows minus 1 times the number of columns minus 1. Again, when I'm saying number of rows and number of columns, that does not count the totals row and column. Okay, very easy to make that mistake and just count all the rows and all the columns. You can't count the totals. We're only talking about the columns that correspond to a category, not the total. Okay? So on our previous one, we had a 3x4 grid. So my degrees of freedom would be 2 times 3 or 6. Everybody's cool with that? So 3 rows, 4 columns. Our degrees of freedom should be 6. Everybody cool? Okay. So now that we have our degrees of freedom, the second thing we need to do is choose a level of significance. That's the alpha. Same idea as the previous 2 tests. If not stated, what's the level of significance assumed to be? 5%. Okay, if it doesn't tell you in the problem, we're assuming it to be 5%. So now that I have a level of significance and I have a degrees of freedom, let's say we picked 10% for our degrees or for our level of significance. I don't know when I did that here. Did I say that in the previous slide? I don't know. Okay, let's just pretend we picked 10%. Again, the idea is with the degrees of freedom and the statistic, we can build out a curve. So if I have 2 degrees of freedom, my curve looks like this, 4, 6, etc. And then the alpha is going to be, okay, if the alpha is 0.1, we're going to shade under the curve where 10% of that curve is covered, wherever that 10% line would be. And if we track down to what the x value that corresponds to the leftmost of that shading, that's our chi-squared calculated value. Everybody's okay with that? And if we plot our, chi-squared critical would correspond to where 10% of the curve is shaded to the right. if we plot our chi-squared calculated value, plot that on the x, and then shade to the right, the percent of the curve covered is our p-value. Okay? So as the chi-squared value gets bigger, the p-value should be getting smaller, right? As your level of significance, your alpha gets bigger, your chi-squared calculated value should be getting smaller, right? Everybody's okay with that notion? I think we talked about this before, but this is I think the hardest to understand pieces is like, what are these things coming from and how, what are they really saying and what's the relationship between chi-squared critical and the alpha and then the p-value and the chi-squared calculated. Like, it's nice to just hear them again and again and again because it's kind of hard. And here, you didn't even know it, but we're doing, like, technically what we're doing there is calculus. You just didn't know it. All right. So we have all this assigned. And if we take our, oh boy, what is this crazy looking picture? Once you have the appropriate curve selected, so with, for example, if the degrees of freedom is 2, and you assign your level of significance to see how much of the curve you shade, so like maybe that's our shading. So again, that represents the chance of getting unrepresentative or bad data. So that's where the bad data lives, over here. And now there's usually low odds of getting that, right? But it's still not 0. So again, at the same level of significance, that chi-squared calculated value, chi-squared critical value will change dramatically depending on the shape of the distribution. Remember, the shape is dictated by the degrees of freedom. So like, this is the same level of significance for 2 degrees of freedom versus 4 degrees of freedom. Look at how the chi-squared calculated value or critical value is changing. Here it's like, 8-ish. Here it was like, a little more than 4 probably. If we have 6 degrees of freedom now, it's bigger than 10, right? We can see that the degrees of freedom really changes for the same level of significance, really changes that chi-squared critical number. Everybody's okay with that? Okay. So yeah, we just talked about what that means. So the blah, 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 blah. We've talked about chi-squared critical before. So comparing these, that's our conclusion. So if your chi-squared calculated is less than your chi-squared critical, we would accept the null hypothesis and by definition then reject the alternative. Or you can say fail to reject the null is fine and reject the alternative. So again, the conclusion here is you want the chi-squared calculated less than the chi-squared critical. Or alternatively, what else can we compare? P-value to alpha, right? And the relationship there is reversed, right? If P is greater than or equal to alpha, we accept the null. Because remember, as the probability, as P goes up, the chi-squared the chi-squared calculated is getting smaller, right? Okay. So the reverse is true then if the chi-squared calculated is bigger than the chi-squared critical. We would reject the null and accept the alternative or fail to reject the alternative. So that's the obvious, converse of the previous statement, right? Now, in practice, we're going to do this calculation more often than not on our calculator, and the calculator doesn't give you a chi-squared critical value, but it sure as heck gives you a p-value, right? So more often than not, we'd prefer to be comparing alpha to p. So again, talking about what p-value is, but we've talked about that before. Blah, 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 blah. So if our p-value is greater than alpha, that means we accept the null and reject the alternative. And again, instead of accept, you can say fail to reject. That's fine. And then again, if the p-value is less than alpha, then we would reject the null and accept or fail to reject the alternative. So if we go back to our problem, so we had 12.6 as our chi-squared calculated, 6 degrees of freedom, 10% level of significance. That's what it would have looked like if we did the draw on the calculator. That's our chi-squared calculated. This was our chi-squared critical. The green is alpha, the red is the p. What do we notice here? P is less than alpha, right? Everybody see that? Or that chi-squared calculated is greater than chi-squared critical, the black line. So we reject the null hypothesis, and we would fail to reject the alternative, which means our two variables are dependent. Everybody's okay? So what should your question be at this point? Mr. Kulik, how do I do this on my calculator? Right? Because that's the, we're not getting a p-value by hand unless you're, a lot about calculus, and none of you want to know how to do the p-value by hand because it is a nightmare. So what do we do? Actually, let's pull this back up here for a second. Okay, that's what I want. You may, but you might want to watch this first, Luke. Just saying.
It's okay, it's not like
Okay.
I just can't go and
All right. So what I'm going to do is if we go to, let's see, we do stat tests, and then we scroll down till we find that chi-squared test. If we look at the inputs, the observed counts, it wants what is it when I have a bracket, what is that object it's asking for? A matrix. So all I'm going to do is I'm going to type in my observed counts table into a matrix. For expected, it wants it as a matrix. So I'm just going to type in my expected counts into a matrix, and then I should be good to go. So second, and then the matrix button. I'll go over to the edit command. This matrix is a 3x4. So just enter this in, 3, 6, 8, 13, 9, 14. Yeah, it's right there under the green button. One down from the green button anyways. But you see it right there now in blue words. 10, 8, 12, 15. Everybody's cool with that? Just entered in the observed counts data from here. Now to do the expected counts, I'm going to do that in matrix B. Again, that has to be 3 by 4. They have to be the exact same size. So to do this, I'm going to do row total times column total divided by overall total, because I want the decimals. So 30 times 28 divided by 110. 30 times 26 divided by 110. 30 times 34 divided by 110. Everybody's okay with what I'm doing? Oops. Times 22 divided by 110. 45 times 28 divided by 110. 45 times 26 divided by 110. 45 times 34 divided by 110. Oh, last row, thank goodness. 35 times 22 divided by 110. 35 times 28. Oops, missed the 2 apparently. 28 divided by 110. 35 times 26 divided by 110. And then my last one, 35 times 34 divided by 110. Woo! That was a workout. Sure. Elise, are we good? Are you sure? Okay, exit out of here, stat, tests, chi-squared test. The good thing is it's all recorded, right? Yeah. And then go ahead. I did my observed in A and my expected in B, so I'm just going to hit calculate. Look, it didn't even make me do the degrees of freedom myself. It did it automatically for me. Ooh! So there it is, and that matches the chi-squared and p-value we reported here, right? Oh, yeah, the 12.6 there. What do you guys think? It's okay? All right. So next time we're going to do we'll do the in-class examples for the chi-squared independence. I have another worksheet for you guys to do with the chi-squared independence. We'll do that next time. The following week we'll do the quiz and the test for these sections.
Don't we only have 2 B days that week? So it's just going to be one class is quiz, one class is test?
Probably.
Right, because next week would have been an A week. Then
Okay.
it's a, oh wait, then it's a B week.
So Monday's an 8A.
Tuesday's a B day.
Tuesday's a B day, then we have no more classes.
And the next week, Monday will be an B day.
We'll be in, no, usually goes A, B, right?
But next week is gonna be AB.
Right, so it ends with a B. So the next week should start with an A.
Oh, I thought it went based on like, cause like technically next week would have been an A week where there's more
Oh,
A's and B's.
I think it always just, whatever the, I think it just alternates days. Yep. You're welcome. Everybody's cool with the plan? Okay. So for yous guys, the only assignment for Sunday's problem set is the 13.1 problems. 13.2 will be a next week problem. Everybody's cool? And we'll have another worksheet, but I think these things that we kind of do mostly in class and turn in are, you guys are fine with,
Yeah.
right? That's not a big deal. Everybody happy? I mean, relatively so. You know, nobody's really happy. All right. I'm stopping everything. Feels good.